Hello, this video is about doing the calculations for the conductivity titration. So let's talk a little bit about the background theory first, just so you'll understand what's going on. So, like all titrations, this involves a reaction between the chemical of interest, the analyte, and some other chemical called the titrant. And the titrant is the chemical that you're going to put in the burette. And so this is a volumetric analysis method. So we're going to measure the volume of titrant it takes to exactly react with the analyte that was in your solution. And these will combine together to produce some products. What we hope is that this reaction is fairly specific to this analyte and doesn't react with anything else in our solution. So in this conductivity titration, our analyte is going to be the chloride anion. So we're trying to measure the salinity of some simulated seawater. And so the titrant that we're going to use is the silver cation, Ag+, and it is also dissolved in water. So we're going to get the silver ion from silver nitrate. So that's the compound that we're going to dissolve in water. And when it dissolves, it will break apart to give us silver cations and nitrate anions. So the silver binds strongly to chloride to form a precipitate, AgCl solid. And so this precipitate is kind of a white solid, but as it stands in exposure to light, it will gradually turn sort of a lavender purple color. And so what we're doing is a precipitation titration then. So we're using the silver, we're adding it from our burette until we've exactly reacted with all of the chloride in our solution. So if we're able to measure the amount of silver that we've added, the number of moles, then we can use it to figure out the moles of chloride that we have, because we see that there is 1-to-1 stoichiometry here. Every 1 mole of silver reacts with 1 mole of chloride. So as we do this titration, we're going to see that silver precipitates out, and that's going to make these little tiny solid particles that are suspended in the water, which is going to make it look cloudy. Anytime you see a cloudy, sort of opaque looking solution, that means you've got little tiny particles suspended in there. That's what makes some dirty lake water look kind of murky. All right, so our titration reaction, this is our titration reaction, and we need some way of measuring when this endpoint occurs. So how do we know when we've added exactly enough silver from our burette to react with all of the chloride that was present in our sample? Well, in this experiment, we do that by measuring the electrical conductivity. Objects conduct electricity because they have charged particles that are able to move around. And in solutions, those charged particles are ions typically. And so in this case, we've got ions like chloride and silver and nitrate that are moving around and conducting the electricity. So let's imagine kind of a simple experiment. So I've got a little wall of metal, so a little piece of metal that I've put on one side and immersed it in a solution. I've got another piece of metal that I put on the other side of a solution. And so inside this region right here, it's filled with liquid. So I'm going to draw some little waves up here. And so inside this liquid then, we've got a couple of different kinds of ions. So we've got sodium cations, let's say, and chloride anions. And what we're going to do over here with this piece of metal is we're going to imagine that we pump electrons into it. And so that's going to charge this piece of metal up so that it has a negative charge. Over here, we're going to be pumping electrons out of this side of the piece of metal. And so if we're losing electrons, then it's going to build up a net positive charge. And so I'll draw little plus signs there for the positive charge. And so what happens is that the sodium cation is repelled by the positive charge and attracted to the negative ions. So it's going to make its way, it's going to migrate this direction. And the same thing is going to happen with the chloride ion. It's going to start moving this direction. And anytime we have moving charges, well, that's what electrical current is. So our charge carriers in this case are these ions. And so what we can measure is how well does this solution conduct electricity. And we call that the conductivity. Now, conductivity is going to depend on a lot of things. So for one thing, it depends on how mobile these ions are. So the mobility of the ions. So since the ions are our charge carriers, we care about how easily they can move through the solution. And that's going to depend on a couple of things. So first off, it's going to depend on, in fact, if you look at one of these ions, they're going to be surrounded by solvent molecules. So in this case, water molecules, but if we were in some other solvent, they might be surrounded by some other solvent molecule. And these water molecules, let's say, they attach themselves pretty strongly to this ion. So as this ion moves around, it's like it has to drag these other water molecules with it. Kind of like a star as they move around, you know, they're surrounded by paparazzi that kind of follow them everywhere. And it makes it hard for them to move very quickly. And so this sets up a size for this particle. And this is the solvated radius, or if we're talking about water, it would be the hydrated radius. Okay, so the mobility of the ions will be affected by the size of the particle. So big particles, right, it's going to be harder for them to move through the solution. So if they have a big hydrated radius. The other thing that affects mobility is the charge density. So you might have guessed that it matters whether we've got a +1 charge or a +2 charge or so forth, and that if we have a bigger charge, we're going to feel a bigger force due to the electric charges on these metal plates over here, and that might produce a bigger force and move us faster, greater acceleration. But it's not just the charge, it depends on how much charge is packed into a given space. So ions have different sizes as well as different charges, and so those charges are packed into different spaces, and so they're going to have different charge densities. Charge density is just the amount of charge per unit volume. And then finally, it matters on how much the solvent resists the flow of these ions. And so a measure of that would be the solvent viscosity. Viscosity is a property that measures how easy it is for liquid materials to flow, right? So things like honey or syrup or oil might be pretty viscous, whereas other solutions might flow really easily, just kind of zip along and not be very viscous. So those things affect the mobility of ions. And so the fact that we have different ions with different mobilities is going to change the conductivity of the solution. So the conductivity then is related to the amount of charge flows per unit area. So if we go back and look at our picture, we might imagine that these charges are flowing through a little segment, a little square. And the bigger we draw this square, the more ions are going to pass through there. So we want to kind of relate it to how big our square is, how big our metal surfaces are. So that's why it's per unit area. So the amount of charge that flows per unit area in a given amount of time. So conductivity is related to that. So that's what we measure with our conductivity meters. So as we are doing this titration, let's think about what happens. So I'm going to draw a couple of different beakers here, showing us a situation at different points in our titration. So initially in our beaker, we've got our solution, our sample solution here, and we've measured out a fixed volume of this solution, and inside this solution we've got some ions. So if this is salt water, then maybe we have some sodium cations and some chloride anions. Now the chloride is what we're looking for. So I'm going to draw a couple of them in here, a couple of sodiums. So we always have a counter ion to balance out the charge. All right, so this is our initial situation. And then as we start to do the titration, what we're going to be doing is adding some silver nitrate into this solution. So we're going to be adding some AgNO3 into this solution. And remember that AgNO3 is made up of two ions, the silver cation and the nitrate anion, NO3-. And so as we start to do our titration, draw another beaker here. All right, so here is the original amount of solution we had that had our sodiums and chlorides, and now we've added from our burette some silver nitrate. So there's now some silver and some nitrate in our solution. And what happens as these begin to mix, a silver ion might bump into a chloride ion, and they're going to precipitate out. So they're going to make a silver chloride solid and precipitate out, and if we let them stand a while, they would actually sink to the bottom of the beaker. So what's left in our solution? Well, we have two sodiums, one chloride now, and just one nitrate. So we've replaced the chloride ion with a nitrate ion. That's effectively what we've done. Now, chloride ions, nitrate ions, they have different mobilities, and so that's going to change the conductivity of our solution. We've also added a little bit of extra volume here, right? So we've diluted our solution down a little bit, and so there aren't as many ions per unit area to be flowing back and forth, okay? So we will have changed the conductivity of our solution when we did that. Now if we continue adding silver nitrate, then eventually we get to this situation. So let's scroll over this way, draw another beaker. And so right at the equivalence point, we have added just enough, so I'm going to call this EQPT for equivalence point. We've added just enough silver nitrate to react with all of our silver chloride. So the sodiums aren't doing anything, they're just hanging out here. And now all of our chlorides have been reacted with silver. And so we've got AgCl solid particles. And again, if we let them sit long enough, those silver chlorides will precipitate out and form a powder at the bottom of our beaker. And so then we've got nitrates in our solution instead. And again, we will have added yet more volume, and so we will have diluted things down, and so there aren't as many ions in our solution to flow around. So right now we have the same number of ions as we had in the beginning, we've just got them in a bigger volume, right? And so the conductivity is probably going to go down. Now, as we continue adding silver nitrate past the equivalence point, our silver nitrate's probably pretty concentrated compared to our sodium chloride solution, and so we end up with lots of silver ions in this solution and lots of nitrates. So our sodiums that we had initially are still there, they're just hanging out, but now we've added extra silver ions and nitrate ions, and so we've got a bunch of those guys floating around in here now that we're past the equivalence point. And so now we're starting to increase the number of ions. We've added a little bit more volume, but now we've increased the number of ions in here. So it might be that the conductivity is going to change again. Maybe in this case, the conductivity goes up. And so if we measure the electrical conductivity with a conductivity meter, we can actually see when we get to this important point, the equivalence point, when we've added just enough silver to react with all of the chloride that we had initially in our solution, right? So that's what we're trying to figure out. Add exactly the right number of moles of silver to react with all the chloride, our analyte, that we had initially in our solution. So if we were to do a graph of conductivity, so I'll abbreviate it that way, conductivity is typically measured in units of microsiemens. That's described with a capital S as the abbreviation, per centimeter. So this would be the typical unit for conductivity. And down here we're measuring the volume of our titrant that we're adding, and so this is the volume of silver nitrate solution that we're adding from our burette. So initially the conductivity, let's say, is pretty high, but then we start diluting the solution and exchanging the ions, and so maybe the conductivity goes down. Now at some point in our titration, that conductivity will start to go back up because we've passed this equivalence point and we start adding extra ions. And so we might see this going on. And if we really kept adding lots and lots of silver, eventually it would kind of level out once it starts to become looking like the silver nitrate solution that we've added. And so what we want to do is take the linear part of these two graphs, so like these points over here, and we see that they more or less fall on a line. So I'm going to draw a little line through those points like that. We're going to call that line 1. And like every line, we can write the equation of that line, y equals mx plus b in slope-intercept form. And I'm going to call this m subscript 1 because it's associated with line 1. So y equals mx plus b, and we're going to call this b1, again, because it's associated with line 1. So now what I'm going to do is we're going to take these other points, and if there are any points up here that aren't on the line, I'm going to leave those off. But the ones that seem pretty linear, I'm going to take those data points, and again, I'm going to find the best line through those data points. And that's not such a great line that I drew, but you get the idea. There we go. And again, we're going to get another equation for that line. We're going to call this line 2, y equals m2x plus b2. There we go. And so we want to find this equivalence point, this place where we've added just the right amount. Well, that's going to be where we change direction in this graph, and that's going to occur right here where these two lines intersect each other. So we're looking for that point where these two lines intersect, and we want to know at what precise volume did that occur. So we're looking for that point. Now, one thing you might remember from algebra class is that we can figure out where two lines intersect because at the point of intersection, they have to have the same y coordinate and the same x coordinate. Now we're interested in the x-coordinate, so what we're going to do is we're going to set these two lines equal to each other. So line 1, we're going to say that m1x plus b1, well, at that y-coordinate, so that equals y, and at that y-coordinate, it equals line number 2, which is given by m2x plus b2. And now we're trying to figure out what x-coordinate occurs where these two line segments intersect. And now we've got one equation and one unknown that we can solve. So let's collect all our variables. I'm going to write this all in red now. So mx1 minus m2x is equal to b2 minus b1. So I just subtract m2x from both sides of the equation and subtract b1 from both sides of the equation. Now over here on the left-hand side, I'm going to factor out my x. So I have an m1 minus m2 times x is equal to b2 minus b1. And then I'm going to divide this term in parentheses by both sides. And so I solve for x. Get it by itself on one side of the equation. So I've got b2 minus b1 divided by m1 minus m2. And so this is our equation that we can use to figure out where our equivalence point occurs. So we just need to do the data analysis where we take the data from our two line segments here, we figure out the slopes and the intercepts, and then we plug them into this equation, and this is going to tell us our equivalence point volume. And so that's what you're always after in titration. You want to figure out the equivalence point volume. And so that's going to be our volume. I'm going to call that V sub EP, right? And that's the volume of our silver nitrate solution. All right, so how do we do the calculations from here? Well, we're looking for the molarity of chloride. And so the molarity of chloride will be equal to the number of moles of chloride that we had divided by the volume of the solution that we took, the volume of our sample. So when we first started doing our titration, we took a certain volume of our sodium chloride solution. We took a certain volume here. Where did we get this? Well, we got it from our sample, and we pipetted that volume into our titration container, the beaker, the flask that we used. So we know this sample volume. This is what you pipetted out, the sample. And let's say that turned out to be 3 milliliters, and we used a 3 milliliter pipette to pipette this as precisely as we could. And so let's say we know what our sample volume is. It's 3 milliliters. So what we need to try and figure out is the number of moles of chloride, and then we can just do the division here and figure out our molarity of chloride. But how are we going to know the moles of chloride? Well, because we did this titration, we know from the reaction that we're looking at way back up here, let's go back up there, that we have this 1-to-1 stoichiometry. So 1 mole of chloride reacts exactly with 1 mole of silver, right, that we've added. And so we can say that the moles of chloride down here will equal our moles of silver added. And because we know our equivalence point volume right here, we know the volume of silver that was added. And so we just need to go from volume of silver to moles of silver. And we could do that as long as we know the molarity of our silver nitrate solution. And we do know that because we mixed up that solution ourselves. We weighed out a certain number of grams of silver nitrate, right? And so from that, we can figure out moles of silver nitrate, moles of AgNO3, using the molar mass. And then we dissolve that silver nitrate very precisely in a fixed amount of volume. And let's say that we use 250 milliliters. So that's 0.250 liters. And so we just do this division, and that will tell us what this molarity is. And so I can use that information to figure out how many moles of silver I had. So let me show you that calculation. We'll just kind of walk through it. So we're going to take our equivalence point volume here for our silver nitrate, okay? And that's going to be in units of milliliters. So this is the number that you measure by solving for that X that we were just talking about. And then we're going to multiply this by our molarity of the silver nitrate solution. All right, so let's say our silver nitrate solution was 0.070 moles of silver per every, and we're going to make this millimoles of silver per every 1 milliliter of solution. All right, so the millis would cancel out, moles per liter, that's still molarity. Now you're going to know your molarity to more than the 2 digits that I wrote here because you measured it much more precisely, but it'll probably be around this number. But you're going to use your exact number. Don't use my number. Use your exact, more precise number. So we're going to multiply that equivalence point volume that we calculated up here with this equation, multiply it by our silver molarity, and then we can use our stoichiometry that says that there's 1 millimole of chloride per every 1 millimole of silver that reacts. And so that's just our 1-to-1 stoichiometry there. And so the millimoles of silver cancel out. Our milliliters of solution have canceled out. And so now we have our moles, our millimoles of chloride. So when you're done with this calculation, you'll know your millimoles of chloride. Then what do you do to figure out the molarity of chloride? That's what we're looking for. You just take the millimoles of chloride that we just calculated. So whatever this number is right here, you plug it in here. That's our numerator, and we're going to divide by the milliliters of sample. And for us, let's say we took 3 milliliters. And maybe you didn't use 3 milliliters. Maybe you used 5 or 4 or 2 or 1 or some different number, but that's what you'll use. And then we'll figure out from that number of millimoles that we weighed out, we'll divide by 3, and that will give us the molarity of chloride. Okay, so that's what we're looking for. And if you did 3 trials, you can then get your average and your standard deviation. And knowing the standard deviation and the number of trials and all that, you can also calculate a 95% confidence interval. All right, and so there's an overview of how we do the calculations. Now I'm going to switch over and show you how we use Microsoft Excel to do this fancy stuff that I was talking about up here, where we find the intersection of this line. So this starred equation right here, and doing all this math. So I'm going to show you how we would do that for one of the trials. So let's switch over to Microsoft Excel. So here's some example data. This data is made up, so your data may look different from this, but this should give you an idea of what it might look like. So for trial 1, what I did is I recorded the volume measurements off the burette, and sometimes I didn't quite hit the mark, so I would record, exactly what I thought the volume was. So you should have these data points out to the 100th of a milliliter. Because the burette's marked off in 10th milliliter increments, we could estimate between the lines. And this is the conductivity measured in these units of microsiemens per centimeter. Okay, so like we talked about previously in discussing the theory, we need to kind of come up with the equations for the 2 lines for this video. So first thing I'm going to do is graph the data. So I'm going to select the data, go up here to the Insert menu in the upper left here. We're going to go over to Charts, and we're going to select the chart type that's the Scatter X, Y, or Bubble Chart option. And we're going to choose the scatter plot. We're going to choose one of these scatter plots like that. Boom. All right, so that's what our data looks like. And as I described previously, the conductivity goes down because we are diluting the solution and adding a different kind of ion that might have a different mobility. And then after we reach the equivalence point, it starts going back up. So looking at where these 2 lines intersect, we estimate that the equivalence point is going to be a little after 10 milliliters. And here we can see that that's where it starts to go down and goes back up. So once we get to the 11 milliliter mark. So somewhere between 10 and 11 milliliters is where that equivalence point volume is, but we want to know what that is more precisely. So we're going to calculate that. So you see I've got 2 line segments here, this first line and this second line, and I want to find their intersection. So I need to get the equation of the line through these data points on the left and the equation for the line for the data points here on the right. So I'm going to call those line 1 on the left and line 2 on the right. So here we go. I've already input some labels here for us for line 1 and line 2. And so what I need to do is have Excel calculate the slope and intercepts for those lines. So slope 1 and int 1 for intercept, for the y-intercept for line 1. So I can use some formulas in Excel to help me do that. So there are 2 functions, slope and intercept, that will give me these parameters. So I'm going to type an equal sign because it's a formula. I'm going to type slope, S-L-O-P-E, open a parentheses, and so you see our little hint down here is telling us that we need to first give Excel the known y values. So my y values are the conductivity values. So I'm going to click and select the y values, but I only want to go down through the 10 milliliter mark, because this line is the decreasing line. Once it starts to increase, I don't want that data point. So those are my known y's. Then I'm going to type a comma, and that lets me go to the next parameter, which are my known x's. So I'm going to click and drag the known x's down through 10 milliliters, where the conductivity has stopped going down, and at the next data point will start going back up. And that's all there is to it. I just hit an enter, and so there's my slope. So it's a negative slope. That makes sense because it's sloping downwards here for this first line. So I need to do the same thing for the intercept. So I'm still looking at this first line, not this second line. Oops. All right, so we're going to type equals here, and then I need to click type intercept. There it is. And then we click and drag the known y. So again, we're still doing the same line. So we drag down through the 10 milliliter mark, type a comma, click and drag down through the 10 milliliter mark for the x's, and then we hit enter. So there's my x-intercept. And if we look at the graph, that makes sense because my x-intercept appears to be right here, right at the 927 mark, and that's about the value that we're getting. All right, so we need to do the same thing for line number 2, so we're going to calculate the slope. And so we select those data points, and then we're going to enter a formula for the intercept as well. So I will go ahead and do those so you don't have to watch me doing those and come back in just a moment. So we're going to, well, let me go ahead and do this one so that you know where we're selecting the data from. So I'm going to click and drag the y data for this second line. So we're going to start at the 11 milliliter mark where the conductivities start going back up. Type a comma, and then click and drag for the x values. We hit enter, and now we're going to do the same thing using the same data but for the intercept. So now we've got the slope and intercept for line number 1 and line number 2, and so we want to find out the x coordinate where these two lines intersect. And so you'll remember we derived an equation for that in earlier, and so I'm going to go ahead and show you that equation. And so that equation was the difference between the two y-intercepts, b2 minus b1, divided by the difference between the two slopes, but this case it's m1 first minus m2. So we just need to enter that as an equation in Excel. So we type our equals sign, then the numerator, we're going to open our parentheses, and then b2, so that's the intercept for line 2. So I just click on that cell right here, E9. And then we're going to subtract from that the y-intercept for equation for line number 1, and that's cell E5 here. So I click on that, close my parentheses, that's my numerator. Then I need to divide here, the division, the slash, horizontal line here. So I use the forward slash to do that. Open parentheses for the denominator, and it's going to be m1, so that's the slope of line number 1, minus m2, the slope of line number 2. And I close my parentheses there and type enter. All right, so there we go. There's our x-intersection in milliliters. So that is the equivalence point volume. So where these two lines intersect is going to be 10.33 milliliters. So that's the number 10.34. We'll go ahead and round that. So that's the number that I will use for my calculations for the molarity. Okay, so then I can do my molarity calculations, and I'm going to start off with that number. So the chloride molarity, I can type in a formula to do that. And so it's going to be the milliliters, you'll remember from our last equation, our milliliters times the concentration of my silver nitrate solution, 0.07. Now, you should use the more precise value that you know. It will probably be somewhere around 0.07, but it'll be 0.07034 or whatever it happens to be. So use your precisely calculated value. Okay, so make sure that you've corrected the mass of silver nitrate that you've weighed out for purity, for buoyancy, and that you've used all your numbers as precisely as possible. All right, good. So we multiply by the molarity, and so that gives us the millimoles of silver, and that's going to equal the millimoles of chloride. So we're going to divide that by the volume of the chloride sample that we took. Let's say for our example we took 3 milliliters, and we just hit enter then. And there's our chloride molarity. So our chloride molarity is 0.24 molar. Type my unit to the side if I want. And so you're going to get a value like this for all of your other trials. You're going to have another set of data for each of your trials. So trial 2 and trial 3, you'll get chloride molarity for each of those. So you can average those three numbers, find the standard deviation, find the 95% confidence interval, and there you go. All right, thanks for watching. Hope that helped with the calculation.